we have immutable maps, which allow us to effectively emulate the JavaScript object without having to have stateful methods on it. We have a JavaScript list that emulates the array, does the same thing for us. We can call methods and expect a consistent return. These are good things, but they're only as reliable as the data that they give them. And actually, Al and I were just talking about this. Part of the problem is that when you use these structures, if you're to use a structure like this, you're probably not going to use it in a pure environment, that is an environment in which everyone is only using these things, right? Because you may decide to write your immutable data structure, and you may use it in your code, but you're not the only one writing the code, right? So other people are going to use it. Other people are going to pass things into it. And one of the problems is that the data that's passed in does not have a high degree of integrity. Let's take an example here. We have a mutable object. It's a regular JavaScript object. We create a list. We pass in that object. Now, we actually modify that mutable object. We make it mutating, set that to true. Now we check the first entry. We verify that it's mutating. And it tells me that my data is mutating, right? Inside of my immutable object. I have an immutable class with data that's mutating in it. It's a problem. It's a problem because I cannot be guaranteed now, 10,000 lines of code later, that the data is in the same shape that it was in when I passed it in. There's no good solution to this. There's no good solution to this. In fact, there are some instances where you may want to allow it to mutate. It's been oftentimes said that while it is possible, and it's actually been mathematically proven that you can do everything with functional, recursive code that you can do with imperative code. While you can, sometimes it's not desirable to. There are some exceptions to the rule. But you cannot always depend upon the data that is being passed into your objects, and in some cases you may actually not want to. So this is a problem. How do we solve it? What do we do with this? Oh, here's another example. In the case of an object, we can modify the mutable object by having a reference to an object within an object. We can modify that second reference, and now we have, again, mutating data inside of our immutable map. So neither one of these things is bulletproof. What are we going to do with it? Well, the first thing needs to be snobbiest. You need to grow a sense of snobbery. That is, you must decide to say, no, I will not allow these things. I will stand up and tell my colleagues, let's try to make this immutable. Let's not shift the state of this if it's possible. Don't provide bad data, and to be meticulous. There are ways to sanitize the data. For one, there's a fundamental problem, both the functions we've written. One of them is in the slice method, the other is in our shallow clone. We've talked about the shallow clone. The slice does the same thing in the sense that it just copies the values. Those values can themselves mutate because that's the way JavaScript is. There are ways to sanitize them. You can write a deep clone function that will effectively sever every node of a possible object from its original and create a virtual clone of it. There are ways to do this. It doesn't work with impure functions. So somebody can pass in a function that is not referentially transparent. That is, it's using stuff that wasn't passed into it, like for instance a global variable. That's an impure function. Those can't be copied, or they cannot be clearly dereferenced. You could do some sort of type checking where you iterate through the values and try to verify that they're immutable. But there is no good solution to this in JavaScript. So really, what this is going to come down to is you being consistent with your usage of the data types, which ideally starts with saying the only way that you use immutable variable or immutable data type of any type is if you have to. If you don't have to, you're going to use an immutable one. That includes when you just create the objects. Because when you pass stuff in, remember, you have no guarantee that the stuff you've passed in can, after the fact, be relied upon. So some degree of distrust is going to be merited in your code even after you've written immutable data types, because you know that JavaScript is fighting you and you will not always win. So let's perform another problem here. We're going to actually see how do we work with immutable data structures in real life. Well, here's a simple problem. We want to count the number of people. We're going to consider objects here to be people. We're going to count the number of people who are aged 21 and up. It's a simple problem, right? We've all done stuff like this. How do we solve it? The old way. You build an array, you for loop through it, and every time you find someone whose age is above or equal to 21, push them onto that array, and then you list the length. Pretty simple, right? How do we do that the new way?
Filter.
Well, that's a very good statement, but we're not there yet. You can do filters, you can do other things. But the new way is, of course, you want to create this new list and then do what?
Reduce.
We don't have a reduce in JavaScript. So we don't have a reduce, we don't have a filter. So what are we going to do? We're going to treat it just like a normal array here, right? We're going to create our brand new list. We're going to do a for loop over these things. And then instead of pushing something onto the old list, we're going to reassign the variable to be the new list, which will just contain the members who are older than 21. You see the major difference here, right? Instead of pushing things onto an existing structure, you're reassigning the current structure to be it plus any new members. So basically we did the same thing, right? We will look into solving this later, but before we can do that, we have to talk about a very hard topic. That topic is recursion. And this is where you put on your brain caps. Hopefully all of the carbs from lunch have worn off, because this is going to get a little bit tricky. If last one was tricky, this will be even more tricky, but I promise you, I will try to be more clear on this section. What is recursion? Someone else here, who can tell me what is recursion?
Functions that call themselves.
Yes, it's functions that call themselves. The invocation of a function from within that same function in order to produce a desired result. So a function foo that calls foo. What's wrong with this? Infinite recursion, right? It's a very, very easy way to end up burning all of your browser CPU. So what is recursion good for? Let's talk about the things that this is well designed for. As with all things, including functional programming, there are things that it's really well suited to, things it's really great for, and some things it's not as great for. It's really good at solving the same type of problem, on the same type of data, for an unknown quantity of data. So let's say you have an object, for instance, that we mentioned earlier, with who knows how many nestings, but you know there's always going to be a key, there's always going to be a value, and you want to infinitely clone each node. That's something that recursion is really good at. It's actually perfect for, because at each one of those steps, you can do the same kind of checking on the same kind of data to perform a single kind of operation. That's where recursion is powerful. It's really good at iterative branching. So an example might be a tree, where there are many possible forks in the tree, and you maybe want one single outcome. Recursion is very good at solving those kinds of problems. You want it when you have large problems that are composed of smaller and simplistic versions of that same problem. So when you can break one big problem down into smaller problems of the same type, recursion is very good at this too. And lastly, it is also quite good at iterating, though it is less efficient, actually, than native JavaScript constructs. So the for loop is incredibly efficient. It's marvelously efficient. Recursion is somewhat less efficient because you have the cost of the function call itself. In fact, you can only recursively call yourself so many times before the browser will blow up on you. So there are limits to the power of recursion in virtually all languages. I think there are 2 that actually fully support tail recursion on all platforms, that you can infinitely call a function without the compiler or runtime errors being thrown.
It's just Haskell and Scala, right?
Now Scala will blow up on you too. I'm afraid Scala will blow up on you too. But Haskell it will not. So let's actually talk about creating a recursive function. Our fourth problem here is to create a for each method. We're going to create a simple loop using recursion. This probably sounds very hard and maybe unknown to most of you, but we're going to do it together, and it shouldn't actually be that bad. We're going to do it without using native JavaScript loops. We're going to create this function that allows an operation to be performed for each element in an array, such that we can call this method for each, pass in an array, give it a function that takes each one of those elements, and it will do something with it. In this case, I'm logging that out. So we're going to write a function for each that we can call this method, and it will in fact log 1, 2, and 3 to the console in sequence. So let's start writing. Project number 4. Raise your hands now if you'd like me to come up and assist. If you feel comfortable getting started, please do so. Of course.
Well, I guess this is much more flexible.
You solved recursion, which is fantastic. We can now move on to more complex things. No, actually we're going to review the function first. For how many of you got your complete for each loop? For eaches are evil, by the way. We'll talk about that later. But that's fantastic. That means that a lot of you are to some degree familiar with recursion. This is actually a hard problem. This is the way I solved it. There are a lot of ways to solve it again. But essentially I check if the array length is greater than 0. That is, I still have at least one entry in there. If it is, then I'm going to invoke the function, and I'm actually going to pass in that element. So I'll call that function on the array. If I've got an element in there, I'll call a function on that. Then I'm going to re-invoke the method after I pull off the first member of that array. I'm going to use a slice to give me every member of that array but the first one. Pass that back into the function along with the original function. So I recursively call until I get no elements in my array, and then I no-op the function ends. This is how you do a recursive for loop in JavaScript. Still confused? Good.
I have a question.
Yes.
I don't really know JavaScript, but does that print it to the console?
This will not print it to the console, no. You'd have to invoke the function after the fact,
Okay.
which I don't think I actually demonstrate here. Yes? You do have pop. Pop is mutative. So you could definitely do pop here. I shunned it because I'm leaning more towards, at this point, the maybe less familiar methods in JavaScript, like slices or concats and things, because I want to get away from any of the possible mutative functions that are available to us. So I'm gonna shun pop, I'm gonna shun unshift and things like that in favor of things like slices here. All right, next problem. We're gonna take exactly the same type of problem, a recursive problem, but this time what we want to do is generate a Fibonacci sequence. You all know Fibonacci sequences are the magic ratio for the world. So what we're going to do is we're going to write a program to generate this thing. The sequence is 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. And you want to write a function that generates this recursively. Now there are functions to do this, and they are long and they are ugly, that do not use recursion. But the best ones use recursion to solve the problem. And the fundamental challenge here is, if you don't know what a Fibonacci number is, a Fibonacci sequence begins with the number 0, and then for every element passed in, for every additional number, like 1 for instance, begins with a 0 and a 1, you add those numbers together to get the next number. So 0 plus 1 is 1, which is the next one in the sequence. And you add that 1 plus its previous number, which was 1, and now you get 2. You add 2 plus 1, you get 3. You add 3 plus 2, and you get 5, and so on and so forth. So you're trying to keep track of the current value and the last value, and you just keep adding those up over and over and over again. So one problem that is composed of a very small problem repeated over and over and over again. There are lots of possible signatures for this. These are two of my favorite. I've got a Fibonacci function on the top. It takes a number of iterations. It takes n, a previous n, and it will return the Fibonacci number for the iterations or sequence or index that you've specified. So iterations is, again, the element that in the Fibonacci sequence that you want to get back. N is the current number. Previous n is the last number. The second is it just takes the iterations and will return you the index for that number of iterations or sequence in the Fibonacci sequence, entry in the Fibonacci sequence. This is a harder problem. but we're going to work through it now. Again, stay in your work groups. See how far you can get on this one. Once you've done this, we get to write our own fold function. And once you've written fold, you are essentially a master of basic functional programming. And you can write all the other methods that people talk about on monads from the fold. So hopefully we'll get there today. If you want help immediately on this one, working through this one, let me know, and I'll come up there and assist. Or you can come down here.
I was trying to find my Fibonacci functions. I did the first one.
You got a Fibonacci function over there?
I did the first one for a code test for, there's a reason why those guys in us are solving these because Alan, I'm sure told you.
Yeah.
Yeah. So
the first one is actually the most efficient.
That's
It's
right.
the most efficient function that you can make.
The first time I submitted my code test to Alan, I wrote it the second way, and then I rewrote it the first way.
Second one is much more elegant, it's simpler,
Yeah.
but it's also much more complex.
Yeah.
Is this useful? Kind of, sort of. It seems like you've got a lot, you know, a lot of this.
Yeah, and it's just, it's probably good for us to it's more useful for everyone. So, yeah, I will start.
All right. We have all successfully now written a Fibonacci number generator. Right? Looks something like that. So let's walk through this line by line. First of all, we're going to set n. I'm just going to go through the first one here. We're going to set n to n or 0. So in the case that they have not set it, we're going to give it a default of 0. The same with preven. And then if iterations are greater than 0, we're going to have a variable current n that represents either, if n is 0, 1. So that'll be our like default case. It'll be the first one that you have to enter outside of a 0. We'll give it a 1 if our current number is 0. If it's not, then we're going to assign it to be the current number, whatever that may be, plus the previous number, which we have already defined up above to be 0 in the case that it's unset. So then we're going to recall our function. We'll pass in iterations minus 1, so we'll do it one less time. We'll pass in that current number, which is essentially going to be current number plus previous number. And then we're going to pass in the original number, which will now serve to be the previous number for the next iteration. Now, if iterations are not greater than 0, we're just going to return the current number. Question?
Just as a little side note, you actually want to flip those. You want the early return before the iteration check.
You can do the early return. Now, why do you say that? Explain.
I've always been taught that you want to exit out of the function as soon as possible when it reaches it. So in the case that we passed in 0,
Mm-hmm.
the else case should hit first and stop the execution of the rest of the function.
So what you were talking about is the value of short-circuiting, yes?
Yes.
Yes. So when it's a good point, which is preventing any kind of calculation or checking in the event that your failure case is reached earlier is a good idea. In this case, I don't do that because I try to balance my logic so it's very obvious what we're doing, and at least visually to me, early returns kind of and short circuits tend to unbalance it. So then you have to try to explain these things. Well, here's kind of an exception. Here's an exception. In this case, the exception is saved for the last, which is in all other cases we return the current number.
Recursion would also lend itself to when EI6 introduces tail recursion, that your fib would be the last call in the branch.
I didn't actually know they were going to be introducing tail recursion. That is really good to hear. So tail recursion means you should effectively be able to call a function infinitely recursively, which you cannot presently do in JavaScript. It will blow up.
You could also just simplify it down into a ternary because iterations will automatically be falsy when it reaches 0.
You're talking about ECMAScript 6 support, or?
Yeah.
Yeah.
Well, either way, the ternaries have been in since ES4.
No, I'm saying, you're saying you simplify this function with another ternary?
Just if not
Oh, yeah.
iterations.
Well, yeah, I mean,
Sure.
Spot.
you can reduce all of that code after the previous n equals into a one line if you wanted to, but this is structured and easy to read.
Yeah. You could do it. It would be ugly, but you could totally do it. And there are advantages to doing that. Now, because we don't have tail recursion, if you try to do this, like if you copy this exact function or you have your own, and you try to do it above like 90 or whatever, it'll blow up on you in the console. And we'll tell you you cannot recurse that many times. So now, an honest show of hands, if this was too complicated for you, raise your hands now. This was frustratingly hard and you don't get it. Okay, there's one honest person in the group. That's two honest people. Because the next problem is we would want to make our list more useful by adding these kinds of features. We don't have time to go through this as a work group, so I'm going to talk you through it really quickly. I do apologize. I would love to walk you through this, as these are building blocks for doing things with immutable objects in smarter ways. So let me talk you through this. Some methods that you want to add to our list class or to a map class, you want something to shortcut or simplify the generation of a new list. That's what an as list method would do. Head, what does that do? It gives you the first entry in an array. Tail gives you everything else. So you think like the head of a snake and the tail of a snake. The tail is everything else. Head will give you just the first entry. The tail will give you a list of everything else. And you're like, well, why do I care about this? Well, you care about it because the last one there fold. Because you can implement most transformations on any data structure using this thing called a fold. It's something that for those of you who were in the workshop earlier on closure is called reduce. And it's a funny thing. It takes a function that takes an accumulator and a value, and you can perform transformations on those things together. So we're going to move through this quickly. There's my asList function. How you get the head is you just return the first one on there. Tail is pretty simple. So I'm going to convert this thing into a list, whatever I get from this. And that converted thing is actually going to be a slice of everything but the head. That's how you get an array that represents everything but the head. We'll just slice everything but the head. That's pretty simple. Your fold is a little bit harder, but not much harder. And yes, this could be written a little bit more shortly. This is probably an easier way to view it, though. How do we use it? Well, we're going to return this thing's tail, so everything that remains of it. We're going to fold into that. We're going to call the function itself, we're going to fold into it the function call on the accumulator, and we're going to pass in the current head, so that gives you the first entry to the array. And then for everything thereafter, we're already inside the tail, that is all the rest of the members of our array, in which we will continue to call that same function that we pass in here at the end. Now, if we don't have a head, that is, there is no current element, then we're just going to return the accumulator. I know I've lost all of you here, so I'm sorry for this. Why does this matter? You remember our problem earlier? We were like, well, how can you do the counting? Well, one simple way to do it is using a fold. You can say list I'm going to pass in, I'm going to call a fold on that list. I'm going to pass in a new list. And then for each element in that list, I'm going to say if the age is greater than 20, I will append that to the accumulator that will be returned. And if it's not, I'll just give it the accumulator. So you can visualize it this way. We're calling a function, and there's a box. And what a fold does is it lets you do stuff with that box, whatever that box might be. In this case, we're going to pass in a list. And also, in addition to the box, it takes one element from the list at a time. So you can deal with it one element at a time. In the case of a function where you want to check for, say, accumulate a series of people who are older than 21, you just say, is this person older than 21? If they are, push them into the box. And you just do that over and over. That allows you to accumulate or transform one kind of list into another. And that is principally what a reduce or a fold is for. It's about taking one kind of data, operating on it one element at a time, and doing something with that and its new container or home. Question? Pardon? Well, that's a very good question. So you can actually implement a filter or a map using a fold. The big difference between a map, for instance, is that you don't actually want to have to think about the accumulator. So in code speak, I don't have it here, I will show you. This is a map implemented in terms of a fold. Here's our fold. Here's your map. You notice that what we're doing is we're just calling fold here, and we're providing the default list here. What do we do inside the function? We return the accumulator, and we append the call of that function on a single element. So a fold is implemented in terms of a map. A filter is implemented pretty much exactly the same way. Any kind of iteration over a data set can be performed via a fold. It's the king or queen of all basic iterative functions is the fold. It's versatile, lets you do almost anything you want on a data structure. We've run out of time. I wish I had given more time for this, but this is a chance for question and answers. I'm going to leave this up. Okay. To say goodbye to you all, which I appreciate your time coming here. Hopefully you've learned something. I do apologize that it was so dense. I will know for next time to slow down the recursion section, do more exercises. But questions and answers, if you have any, now's your chance. All right, so one question for you then. Are you convinced of the value of immutable data structures? Yes? Are you going to try to fight mutation? All right, go forth, code well. Thank you all for coming.